Okay, we are looking at finishing up the practice problems for module number 3. The last time we were together, we got through the very first two practice problems. So we want to do one more that is going to be utilizing the rectangular component method to solve for some unknown forces. And then we're also going to continue to implement our conditions and equations of equilibrium. So I have underneath my camera here, the last practice problem that we're going to be looking at. This is sample problem 2.6. It's on the bottom of page 42. It starts here and it goes to the next page. So we'll start by looking at the illustration and seeing what we're going to be doing for this problem. So for this sample problem, for a new sailboat, a designer wants to determine the drag force that may be expected at a given speed. To do so, she places a model of a proposed hull in a test channel and uses 3 cables to keep its bow on the center line of the channel. So here's the boat's hull. And then here are the connectors to the front there. So we're going to have a cable going up to C, over to B, and then from A down to E. And it's keeping that in the same spot. And what's happening is the flow then is going to be a force that's going to be on that hull. Okay. They said that it says here that a dynamometer, is that how you say that? Dynamometer. Readings indicate that for a given speed, the tension is 40 pounds in cable AB, so right here, 60 pounds in AE, all right. And they want us to determine the drag force exerted on the hull and the tension in AC. So they want us to know what is the force going to the right here. So this flow, it's going to produce a force that's going to be going to the right along that x-axis. So we need to know what that is. That's going to be the drag force. And then also, what is the force in the cable going from A up to C? Okay. So as you can see here, we have what we would we have a concurrent force system. So we have everything coming together here at point A. So we're going to be seeing this kind of coming together like many of the problems that we've been seeing, but we've got a couple extra forces here that we're going to be dealing with. Okay. So what we're going to do is we're going to first start by drawing our free body diagram of what we have going on here. So, oops, I got to grab my protractor out. And we're going to start by drawing a nice generous diagram with an X, Y coordinate system here. So I'm going to make this a little bit larger. Okay. And so I'm going to draw vertical and horizontal. So I haven't converted many people over to making nice big diagrams, but I will tell you, as you're doing your work, it's so much easier to add labels and to read it in the end if you do so. So sample.
This part is not to cram it all at the bottom of the page.
Yes, don't cram it at the bottom of the page. Did you know that they make paper every day? They do. They do. They make paper every day, and people are employed to do it. So you're keeping people in business up in Green Bay. So it's all good. It's all good. Yeah, they got a lot of paper plants up there. All right, here's our y-axis, our x-axis. At the center here is going to be our A, okay? And then what we're going to do is I'm going to start by drawing the different connections, if you would, up to the right, which is going to be C. So I'm going to start by, actually, it's a little bit more steep. So I'll try to make this as close as possible. Okay, that's going to be my A to C. Then I've got my A to B. I have my A to E going straight down. And then we do know that that force, which is going to be the drag, is going to be a vector that's going to push on that hull. So going along that x-axis to the right is going to be that drag force. Okay. Now, in this problem, they call this FD, so the drag force. So I'm going to call it that as well. Now, all I did right now was I showed the cables in place. Now, each one of these cables is in tension. So from that origin, these are all going to be pulling away, okay? So we're going to show arrowheads going up and to the right, and this is going to be C. We're going to have going over and to the left. This is going to be B. And going straight down is going to be E. Okay. Now, you'll notice on here, they did not give us any angles. So we need to calculate the angles based on the distances that are given there. So you'll notice they have angle alpha. And that is going to be opposite the 7 feet. And then this is going to be 4 feet here. So that's going to be like a right triangle. And those are the 2 legs. Then we've got the 2 legs of 4 feet and 1.5 feet for beta. And I think those are the only 2 angles that we need to know. So we need to figure out those 2 angles. So go ahead and calculate beta and alpha. And we'll see what we end up getting. Make sure that we can all get the same answer. So I'm going to kind of do it on the side here, but I'll keep this up here in case you need to look at the illustration. Okay, so find angles alpha and beta. So you should get alpha equal to 60.26 or 60.3 degrees and beta equal to 20.56 degrees. Okay, and that matches what the book has. I rounded mine to 1 decimal and then I saw they had 2, so I'll use 2. Okay, any questions on those so far? Okay. Now, knowing those angles then, am I done with my diagram? Am I done with my diagram? Not yet. What else do I need? I've got my convention. What do I need to do here? Before I go to calculating my components, what do I need to do up here? Yes. Yes, show them, right? Drawn on the X and Y axis. So go ahead and do that for each one of the forces that is not currently on the X and Y axis. So for B and C, we need let's see, an X component for each and a Y component for each. Now we don't know the length of C and B, so I mean, you kind of make those arbitrary because that's what we'll be solving for. We do know their angles, we do know their magnitudes, but now we have to find we do know their direction, but we have to find their magnitudes. Okay, now are we ready to go to step number 2 and calculate or determine the resultants? Yeah, we are. Okay, so let's go to step number 2. This will be the components. Okay, so components, I'm going to start with B just because it's before C in the alphabet. And I'm going to say BX going to be equal to, now, in this case, my alpha is not kind of that standard placement of the angle. So if I look at the B component, it's down here along that x-axis, make sure it's there and it has an arrowhead and it's labeled, but the angle I have would be the side opposite being equivalent. Do you see that? Bless you. Okay, so that means that this would be the sine of alpha, which is 60.26 degrees, times B, which is the hypotenuse. Okay. So what we're going to do is we're going to get this in just decimal form, 60.26, hit the sign button, and BX is going to be equal to 0.8683 times B. Okay. Now we don't know what B is. That's why we have to leave it in variable form. So we'll do that very same thing for the Y component. So this time my BY, again, because of that placement of alpha, that's going to be the side adjacent. So that'll be the cosine of 60.26 degrees times B. So BY is 0.4961 B. We'll just leave it right there in that form. And we'll do the very same thing for C. So we'll find CX and CY in terms of their hypotenuse. So go ahead and do that same thing. Watch your angle beta. See it. Oh, wait, I am mistaken on this. You guys, I do know some of these, don't I? You guys, we do know B. We know B is equal to 40. You know what? I'm sorry. I was I don't know. These a lot of times we don't know these, right? And then this one is AE is 60 to 60 down here. This is equal to 60 pounds. I am so, because I'm looking at this and I'm looking at the problem. I'm like, wait a second, we have way too many unknowns here. We do know B is 40 pounds, don't we? AB is 40 pounds. So that means, I am so sorry. This can be times 40 pounds. And it's going to have an actual number. And this is going to be times 40 pounds. And this is going to be a number. Wow. We were doing in the previous statics class, and it's an excuse, I'm sorry. But we were doing some of the application problems, which were all like that. And I didn't even think to yeah, my brain was somewhere else. Yes, we'll call it a brain fart. 34.731 pounds. Okay. And then, so this one will have an actual number for BX. 60.26. And that's cosine. It's 40. And that's 19.843 pounds. There we go. But C does remain in terms of its hypotenuse because we don't know what C is. We don't know what C is. Our unknowns are C and that drag force. So does that make sense, everybody? I am so sorry. So we know BX is 34.3.731. And our BY is 19.843 pounds. Kind of sneak it in there. So for those of you who make real small diagrams, gosh, I don't know how to do it. And I can
What the
usually,
hell are you doing here?
what was that?
Oh, my bad.
Oh, that's okay. That's okay. All right. Are we all on the same track now? We've got B solved for an actual number with pounds. Good. Well, now, as we look here, our unknowns are FD, drag force, and C. So what's our next step? What do you think our next step is going to be? Go ahead.
Some of the forces in the X and Y direction.
Yes, and we are going to call that the equations of equilibrium, right? We have a condition where this is all balanced out. All the forces have to equal 0. So we're going to use our equations of equilibrium and see how that can help us. Bless you. So our equations of equilibrium, as James had alluded to, are the sum of the forces in the X equal 0, right? What's our other one? Yes, sum of the forces in the Y equals 0. I look for those two equations to like start the process. Okay, so make sure before you start writing anything that you tell me what you're going to do first. Okay, so let's write our equation of the sum of the forces in the X direction. So what that means is we're only going to look on the X axis. This is why we put these components on the X axis or on the Y axis. So now I'm looking only what's on the X axis because I'm summing the forces in the X direction. And you'll notice that I have a negative BX or a negative 34.731. I have a positive CX and I have a positive FD, right? Now, why did I call them positive and negative? Because of my convention. Excuse me. Make sure you have your convention at the top right-hand corner of each one of your problems. I always look there. Okay. If not, I take points off. Okay. So make sure that they're there. Okay. So let's write this equation. I know that I have a negative 34.731 pounds. That's my BX. I have a positive CX and a positive FD. Now, remember, this is an equation of equilibrium. So we have to set this equal to 0 in this first line. I look for that as well. Okay, we don't just randomly, like, it doesn't just magically appear at the end. Okay, this is an equation of equilibrium. It needs an equal sign and it needs two sides. And my other side right now is equal to 0. So now my two unknowns here, I'm going to leave those on the left-hand side and I'm going to move that 34.731 over to the right. So I'm going to say CX plus FD is equal to 34.731 pounds. Make sure you have your units along with it in all phases of the problem. If you want to use LB for pounds, that's totally fine. So I'm going to leave it there. I've got two unknowns. I can't go any further. I'm going to go over to the other side. This one is sum of the forces in the Y direction equals 0. So now I'm going to go back up to my diagram. This is why your diagram is so important. I'm going to look what's on my Y axis. I can see I have a positive BY, which is the 19.843 pounds. I've got a positive CY and I've got a negative 60. Okay. Those are the only ones that I'm writing. So I've got a positive 19.843 pounds, positive CY, and a minus 60 pounds. Equal to 0. Okay, equal to 0. So now I can combine these two, right? I can combine those two and I can say, all right, 60 subtracted from there, that's going to be a negative 40.1574 plus CY is equal to 0. Or move this to the other side, right? Oh, pounds, add my pounds, move that to the other side and CY is going to be equal to 40.1574 pounds. You just solve for it. Well, that's not nice. But that's just the Y component. That's not the tension in the cable, is it? So remember, I need to know what C is from A to C, not just what the Y component is, right? So we're not as close as we think, but we were able to solve for that variable. So how would we calculate for C here? Go ahead.
Put in the equation.
Yes, we could put CY right back up in here, right? And we could then solve for C by dividing both sides by the 0.963. So let's go ahead and do that. I'm gonna go to my next page here. Okay, so we're gonna continue with that equation. So we know that CY is equal to 0.9363 C. And we can then say that 40.1574 pounds is equal to 0.9363 C, right? So now solving for C, I'm going to divide both sides by 0.363. And we should get C is equal to 42.89 pounds. You look to the very end of your problem on page 43, the tension in AC, we just called it C instead of tension in AC, 42.9, 42.89, right? Same thing. So we got it. Everybody kind of follow that process so far? All right. Now we're not done because we still need to find that drag force, right? So we've got C done, but now we've got to find that drag force. So if we go back over here, okay, you'll notice that we still need to find the drag force and CX, right? So as we look at this equation here, we can plug in what we know. We know that CX is equal to what? 0.3512 times C, right? So if I go back over here, that's 42.89 pounds plus FD is equal to 34.731 pounds. So now I've only got the one unknown, right? So I can multiply this out, move it to the other side, and solve for FD. So I'm going to be 34.731 pounds minus 15.063 pounds. Because I multiplied those two together and I moved it to the other side, so I had to subtract it, right? So my FD is going to be 19.69. I'm sorry, 19.67 pounds. Now this one, we didn't end up doing two equations, two unknowns, because we were able to solve for CY along that Y axis and then plug that back in and then plug it in over on the X side to solve for the CX component. And then FD was our only one. Yes.
Go back to where you were solving. For this one.
This one here.
Yeah.
So this was the component that we solved for. So CY was equal to. So we used this CY and we plugged it in right there. And then we solved for C. And then we got C, and then we took this C and then we substituted in where we had the CX and we put the C right there and we said 0.3512 times 42.89, which was C, plus FD. So FD was our only unknown. Yep. Anyone else have any questions? Okay. So that's the last problem in our practice problems that I wanted to go through with you guys. So you would be ready now to hand those in. Okay. And again, paying special attention to the formatting and the things that we've been doing here. Labeling, creating a good free body diagram, convention, arrowheads, units, showing your work, cancellation, all that stuff. Okay. So I'm going to stop here and then we're going to start looking at some of those application problems.